Welcome viewers. Today we are going to discuss functions of a complex variable. This lecture is in continuation to my earlier lecture on the same topic, where I had discussed functions of a complex variable, their limit, continuity, differentiability and analyticity of functions of complex variables. There I have introduced some elementary functions like powers of z, polynomial functions, rational functions, irrational functions and transcendental functions I am going to discuss today. In this I will be discussing exponential functions, logarithmic functions, circular functions and hyperbolic functions. I will also be discussing mapping by elementary functions of complex variables, and finally conformal mapping will be discussed in this lecture. We start with exponential function. The function Ez, the exponential function Ez, we define it as Ex plus Iy as Ex multiplied by cos y plus I times sin y. We have defined this function in a manner so that when z becomes x, it is the usual exponential function of a real variable. So when we take y is equal to 0, then z becomes a real variable and then Ez is the same as Ex, and when x is equal to 0, then this definition gives us Eiy is equal to cos y plus I sin y, and this is known as Euler's formula. Since cos y and sin y, they are functions of real variable y, so we can write down cos y as 1 minus y square by factorial 2 plus y4 of factorial 4 plus and so on. So this is the cosine series. Similarly, we write down the sine series here, and it is y minus y cube by factorial 3 plus y5 by factorial 5 minus and so on. If I combine these terms, then Eiy is equal to 1 plus Iy plus this minus y square is written as Iy square by factorial 2 plus Iy cube by factorial 3 is coming from this, then y4 by factorial 4 is written as Iy raised to power 4 by factorial 4 and so on. So if I arrange these terms in this particular manner, then one can see that this is nothing but expansion of Ex where x is replaced by Iy. So this is very similar to what we have for real variables. Now if in the same formula I substitute minus y for y, then the Euler formula Eiy is equal to cos y plus I sin y, and this substitution will give me E minus Iy is equal to cos y minus I sin y. Adding these two equations, I will get cos y is equal to half Eiy plus E minus Iy. So that is how we relate cosine function of a real variable as this. Similarly, if I subtract, then sin y is obtained as 1 upon 2i into Eiy minus E minus Iy. Using this, we can extend this idea to cosine function of a complex variable z as half of Eiz plus E minus Iz, and sin of z is 1 upon 2i into Eiz minus E minus of Iz. So that is how we introduce the concept of sine and cosine functions of complex variables z. This is in terms of exponential functions. Once we know what is cosine z and sin z, we can write down tangent z as sin z over cosine z, cotangent z is 1 upon tangent z and so on. Again, if we write Ez is equal to Ex multiplied by cos y plus I sin y by the very definition of exponential function of z, then one can notice that this function satisfies CR conditions, like here u is Ex cos y, the real part, and the imaginary part v is Ex sin y. So if we apply CR conditions, we can see that Ux is equal to Vy and Uy is equal to minus Vx in this case, and that simply means that the function is analytic because these conditions are satisfied everywhere, and on the basis of this we can say that d by dz of Ez exists and it is computed as ux plus ivx, and substituting ux and vx from this we can see that this derivative is equal to Ez. So, we have a result that derivative of Ez is Ez. Now, this is also in line with function of a real variable where derivative of Ex is equal to Ex. Similarly, the magnitude of Ez is magnitude of Ex plus Iy, and this is written as Ex into Eiy. So, their magnitudes are multiplied, and the magnitude of Eiy is cos y plus I sin y magnitude, and this is equal to 1, and that gives us magnitude of Ez is equal to Ex. Similarly, the argument of Ez is equal to y. One can also notice that magnitude of Ez is always positive and Ez is not 0 for any value of z. We can define E minus z as E minus x multiplied by cos theta minus I sin theta. What I have done is I have replaced z by minus z. So, this x becomes minus x, and due to minus y, this minus y will appear. So, we have E minus z is equal to E minus x into cos theta minus I sin theta. If we can multiply Ez and E minus z, this is equal to E minus x plus x multiplied by cos theta minus I sin theta plus cos theta plus I sin theta. Multiply the two, it is cos square theta minus I square sin square theta, and because minus I square is minus 1, so we will have cos square plus sin square theta from this product, and ultimately we will have E0 which is 1. Now, this is also in line with real variables. Further, if we say e raised to power 2 pi I, so real part is 0, the complex part y is 2 pi. So, if I write y is equal to 2 pi in our Euler formula, then this will be 1, and e raised to power pi I and e minus pi I both are equal to minus 1. One can also get e I pi by 2 as I, and e minus pi I by 2 is minus I. Further, e z plus 2 pi I is equal to e raised to power z multiplied by e 2 pi I, and since e 2 pi I have already proved it to 1, so I can say e z plus 2 pi I is equal to E z, and from here one can notice that exponential function is periodic function of period 2 pi I. This period is imaginary. So, in this sense exponential function is periodic. Now, let us solve this equation E z is equal to minus 2. One can write E z is equal to minus 2 as minus of E z is equal to 2, and minus of E z can be written as E z plus I z, and 2 I am writing as e raised to power log 2. 2 is a real number, so this can also be written as e raised to power log 2 because exponential and log are inverse functions. So, from here if I compare, then z is equal to log 2 minus I pi, or in general it is z is equal to log 2 plus 2n pi I have added because it is a periodic function. So, it is I times 2n minus 1 pi, and this gives me x is equal to log 2 is a real part, and y is equal to I 2n minus 1 pi, and n can take values 0, 1, 2 and so on. So, this is the solution of given equation. We will continue with this definition. Cos x is equal to e I x plus e minus I x by 2, sin x is equal to e I x minus e minus I x by 2 I. and cos z is equal to eiz plus e minus iz by 2 is just an extension for this, and from here sin z is equal to eiz minus e minus iz over 2i. From these formulae one can easily notice that cos of minus z is the same as cos z and sin of minus z is equal to minus sin z. From here you can notice, and since cosine and sine are expressed in terms of eiz and e minus iz, and since we have already said that eiz and e minus iz are analytic functions, so their sum will also be analytic and divided by 2 is also analytic. The same way sin z will be analytic. So, we conclude that both sin z and cos z are analytic functions of z. Further, tan z is analytic except for the points where cos z becomes 0, because at those points tangent z will not be defined. So, d by dz of cos z is equal to minus of sin z. One can easily differentiate this and that comes out to be minus sin z, and using this formula d by dz of sin z comes out to be cos z, and one can again write down tangent z as sin z upon cos z, and with some simplifications and manipulations one can obtain d by dz of tangent z is equal to sec square z. Here one may notice that these formulas are very similar to what we have for real variables, because we know d by dx of cos x is equal to minus sin x, d by dx of sin x is equal to cos x, d by dx of tangent x is equal to sec square x. So, derivative of sine cosine functions of a complex variable are the same as what we had earlier for real variables. This is not all, other formulae can also be proved in the same lines. And from the way we have defined sine function and cosine functions, one can further notice that these functions, sine and cosine functions, are also periodic functions and they are of period 2 pi. You can check it. Cos z plus 2n pi is equal to e I z plus 2n pi plus e minus I times z plus 2n pi divided by 2, and since exponential functions are periodic, so this part is written as simply eiz and this part is written as e minus iz, and this gives me cos z. So, cos z plus 2n pi it gives me cos z. This proves that cos z is periodic function. You can similarly prove sin z is also a periodic function, and in fact all the formulae which we have obtained in trigonometry using real variables, these formulae can be developed for complex variables also. I will take some examples. Let me consider this product Ez1 into Ez2. I write down Ez1 as Ex1 cos y1 plus I sin y1 by the definition of Ez1. Similarly, Ez2 is written as Ex1 cos y2 plus I sin y2. If I multiply these two terms, I will have Ex1 into Ex2 is common, and this is multiplied by this, and cos y1 cos y2 minus sin y1 sin y2 is the real part, and this is nothing but cos y1 plus y2 plus I times, if I collect the imaginary parts in the product, it will be sin y1 into cos y2 and cos y1 into sin y2. This is nothing but sin of y1 plus y2. So, this is written as Ex1 plus x2 plus I times y1 plus y2, and that gives me Ez1 plus z2. So, this formula is also very similar to what we have for real variables. Ex1 multiplied by Ex2 is E of x1 plus x2, that is the corresponding formula for real variables. So, this formula is also applicable for complex variables. So, this is what we have. Then cos square z plus sin square z is also 1 can check from here. I am writing 1 upon 4 e I z plus e minus I z whole square for cos square z, and this is written for sin square z. We can expand these two and it comes out to be e to I z plus 2 times e minus 2 I z by expanding this, and from here I will be getting e to I z minus 2 plus e minus 2 I z, and we can see that these terms will get cancelled and we will have 2 plus 2, that is 4, and this 4 and 4 will get cancelled and we will have 1. So, similarly we can develop all those trigonometric formulas which we have studied for real variables. They can be proved for complex variables. Then we come to logarithmic functions. Logarithmic function is defined as the inverse of the exponential function. So, we write w is equal to log z, then z is equal to e w. So, that is how we write that logarithmic function is inverse of exponential function. So, from here if we multiply EW1 and EW2, then it will be equal to EW1 plus W2. You can check, this is nothing but log Z1. If we take the log of this, then it is log of Z1 into Z2 is equal to log of EW1 plus W2. We can simplify it and it comes out to be log Z1 plus log Z2. We can express this function in polar form. So, log of Z is equal to log of Z I am writing as r cos theta plus I r sin theta. So, log of Z is log of r cos theta plus I r sin theta, and since cosine theta and sin theta are periodic functions, so I write log of r cos theta plus 2 n pi plus I sin theta plus 2 n pi, and this can be written as log r e I theta plus 2 n pi, or I can rewrite it as log r plus I times theta plus 2 n pi, and n is an integer in this case. So, this gives me the log of z in polar form. One can notice from the earlier formula that log z has infinitely many values, and the principal value of log z is written as log of z. Notice the difference. This is equal to log r plus I theta, where theta varies from minus pi to pi, or sometimes we take theta from 0 to 2 pi. One can also calculate the derivative. D by dz of ln z is equal to 1 upon z, and then we can define the function z raised to power c as e times c ln z. So, z raised to power c is defined as this, and since this function is multivalued, so zc is also multivalued. So, we can define zc in terms of log function. So, z square, z cube etc., they are defined as repeated multiplications, but if c is a different number, not necessarily 2, 3 or a real or a natural number, then we can define z raised to power c in this particular manner. So, since I said that zc is a multi-valued function, so it will have a principal value, and for principal value we write zc is equal to e raised to power c l n z. So, this is the principal value of z raised to power c. We, after defining trigonometric functions, we can define inverse trigonometric functions, and they are defined the same manner as that for real variables. That is, w is equal to sin inverse z means z is equal to sin w, and w is equal to cos inverse z implies z is equal to cos w. We can we are here defining hyperbolic functions. They are defined as sin hyperbolic z is equal to half of E z minus e raised to power minus z, and cos hyperbolic z is defined as half of E z plus e minus z. And once we have defined hyperbolic sine and cosine functions, we can define other functions also. Tangent hyperbolic z is sin hyperbolic z divided by cos hyperbolic z, cot hyperbolic z is 1 upon tangent hyperbolic z, sec hyperbolic z is 1 upon cos hyperbolic z, and cosec hyperbolic z is 1 upon sin hyperbolic z. On the basis of this, we can prove the same formulae. Sin square z plus sin square z is equal to sin cos square z plus sin square z is equal to 1, and one can prove on the same lines that cos hyperbolic square z minus sin hyperbolic square z is equal to 1, and this is what we have for real variables also. So, in place of x, in place of z, suppose we have x, then this is the formula which we have already developed. Similarly, one can write down cos iz is equal to half of eiz plus e minus iz, and this is nothing but half of e minus z plus ez, and that gives me cos of iz is equal to cos hyperbolic z. Similarly, sin iz is I times sin hyperbolic z, that is how we relate the trigonometric functions and hyperbolic functions. So, cos hyperbolic z is cos z, and sin hyperbolic z is sin hyperbolic iz is equal to I times sin z. We can further prove the formulae which we have done for real variables for hyperbolic functions also. Sin hyperbolic z of z1 plus z2 is equal to sin hyperbolic z1 cos hyperbolic z2 plus cos hyperbolic z1 into sin hyperbolic z2. So, all these are the formulae which we have already discussed in our school days, but that they were for real variables. Now, we have for complex variables. So, all these formulas can easily be established. After that, we discuss inverse hyperbolic functions. W is equal to sin hyperbolic inverse z implies z is equal to sin hyperbolic w, and w is equal to cos hyperbolic inverse z implies that z is equal to cos hyperbolic w, and from these definitions one can easily prove that sin hyperbolic z plus pi I is equal to minus sin hyperbolic z. This is how we prove this result. Now, in this example, I will show that tan hyperbolic inverse z is equal to half of log 1 plus z over 1 minus z. To prove this, I consider tan hyperbolic inverse z is equal to w, and from here we can say z is equal to tan hyperbolic w, and tan hyperbolic is sin hyperbolic w divided by cos hyperbolic w. So, this is the formula for I have for sin hyperbolic, this is for cosine hyperbolic. Then we simply simplify this expression as 1 plus z over 1 minus z is equal to E w minus E minus w plus E w minus E minus w, and similarly this denominator is 1 minus z, and simplifying it, this gives me E to w. Taking log on both the sides, we will get log 1 plus z over 1 minus z is equal to 2w, and simplifying it, w is equal to half of log 1 plus z over 1 minus z. So, this is what we have to prove. So, that is how we apply various operations on tangent hyperbolic functions and log functions. Now, many times we need to separate the real and imaginary parts of a function. So, I will give some examples to illustrate this. So, let us say we have been given z raised to power n, and we have to express it in its real and imaginary parts. So, to do this, let me write down this as x plus I y raised to power n, or I write it as r cos theta plus I sin theta raised to power n, and expanding it, it is r raised to power n cos n theta plus I r n sin n theta, where r is equal to under root of x square plus y square and theta is equal to tan inverse y by x. So, this function has real part as r raised to power n cos n theta and imaginary part as r n sin n theta. Similarly, E x plus I y can be written in real and imaginary parts as E x cos y plus I times E x sin y. So, real part is E x cos y and imaginary part is E x sin y. log x plus iy is log of r cos theta plus ir sin theta, and this can be written as log r into e raised to power I theta. Taking log, we can say r is the real, log r is the real part and theta is the imaginary part of log x plus iy. Then sin x plus iy can be written as sin x cos iy plus cos x sin iy, and from here sin x is equal to cos hyperbolic y, and sin iy I write it as I times sin hyperbolic y. So, that gives me imaginary part as cos x sin hyperbolic y. Similarly, cos x plus iy is expressed as cos x cos hyperbolic y as the real part and sin x sin hyperbolic y as the imaginary part of cos x plus iy. Cos hyperbolic x plus iy is equal to cos hyperbolic x cos hyperbolic iy plus sin hyperbolic x into sin hyperbolic iy, again making use of the definitions which we have already given for hyperbolic functions. I write cos hyperbolic iy as cos y. So, real part of this function is cos hyperbolic x cos y, and from here we get the imaginary part as I sin hyperbolic x into sin y. So, this is how we can separate out the real and imaginary parts of some elementary functions. Then complex power of a complex number. So, let us say I have a number x plus iy and here the power is alpha plus I beta. So, this can be expressed as e raised to power alpha plus I beta into log of x plus iy. This I have already discussed that you can express this in terms of log function. The function will have infinitely many values because this value will be multi-valued and the principal value is taken most of the cases. Let me illustrate this with a simple example, I raised to power I. How we simplify I raised to power I as e exponential of I times log I. Actually, I raised to power I is e raised to power I raised to power I, and I raised to power I am writing as I log I. So, simplify taking log I log I is equal to I log of, this is nothing but cos 2n plus half pi plus I sin 2n plus half pi. I am writing the general value here and simplifying it, it is e I times log e 4n plus 1 pi by 2, and this is simplified as I square 4n plus 1 into pi by 2, which can be further simplified to minus 4n plus 1 multiplied by pi by 2. From here we write down I raised to power I is equal to exponential of minus 4 n plus 1 multiplied by pi by 2. The next example, the function sec x plus iy is expressed as a plus ib. That means, we want to write down this function in its real and imaginary parts. So, first sec x plus iy is equal to 1 upon cos x plus iy, and then I multiply numerator and denominator by 2 cos x minus iy, and this on simplification gives 2 cos x cos iy plus 2 sin x sin iy, and this we apply CD formula here. It is cos 2x plus cos 2 iy, and this means sec x plus iy is equal to 2 cos x cos hyperbolic y here divided by cos 2x plus cos hyperbolic 2y plus I times, I is coming from this, and 2 sin x sin hyperbolic y divided by cos 2x plus cos hyperbolic 2y. So, this is my A and this is B. So, sec x plus iy is expressed as real part plus I times the imaginary part. For the second part, tan inverse x plus iy, we take A plus ib is tan inverse x plus iy, and we write A minus ib is tan inverse x minus Iy. Then adding these two will get tan to A is equal to tan of tan inverse x plus Iy plus tan inverse x minus Iy. So what I have done is I have added and then taken the tan on both the sides, and after that this is expanded. So it is x plus Iy plus x minus Iy divided by 1 minus x plus Iy into x minus Iy. Adding will have 2x in the numerator, and this will be simplified to 1 minus x square minus y square. So from here we can say 2a is equal to tan inverse 2x over 1 minus x square minus y square, or a is equal to half of tan inverse 2x over 1 minus x square minus y square. So that gives me the a part, and to calculate b part I will subtract the 2. So it will be tangent to IB is equal to tan of tan inverse x plus Iy minus tan inverse x minus Iy. Then I apply the formula, and this gives me 2 Iy divided by 1 plus x square plus y square. So when I simplify it, I will get this, and on the left hand side I will have I times tangent hyperbolic 2b, because tangent to IB is I times tangent hyperbolic 2b, and from this I can say b is equal to 1 upon 2 tangent hyperbolic inverse 2y divided by 1 plus x square plus y square. This I will get cancelled with this, and then further simplification will yield me the imaginary part b as this. So I have obtained a and I have obtained b. So tan inverse x plus Iy is expressed as a plus Ib. So this is what I have written here. This is a plus I times b. In the next example, we solve cos z is equal to 2z is a complex variable. So cos z, we write it as Eiz plus E minus Iz by 2 is equal to 2, and then we can write E minus Iz, we can write it as 1 upon Eiz and simplify this equation. It will give me Eiz square minus 4 times Eiz, this is the term which is coming from the right hand side, plus 1 equal to 0, and this is a quadratic in Eiz. So Eiz is equal to 2 plus minus under root 4 minus 1, and that means Iz is equal to log 2 plus under root 3 plus 2 n pi I, this is the general expression, and z is equal to 2 n pi minus I log 2 plus minus root 3, or we can say it is 2 n pi minus plus log 2 plus root 3. So this is the general value for z which will satisfy this equation. Now we will discuss mapping by complex functions. So let us consider a complex function of a complex variable z. So w is a mapping from z plane to w plane. So we write w is equal to f of z, and we express this function as uxy the real part and imaginary part is vxy. Now when we define this function, then what we are doing is we are taking a point in z plane and that will map to a point in the w plane. But when we take continuous real functions y is equal to fx of a real variable, then we know that it represents a curve in xy plane. So we want to see how curves in z plane will map to curves in the w plane. So set of points in z plane map to set I of w plane. So let us consider the set S of points in z plane, they will map to an image I of w plane. So if the set of points lie on a curve, then how the mapping will be done, or what is the relationship between two sets in two different planes. So let us say S is the domain and I is the image of mapping, and we have a function f from S to I. For specific properties, we consider curves in z plane and their images in w plane. So this is what we are going to do or next of the examples. Now, to describe this, we discussed level curves. So, the level curves are x is equal to constant, these are horizontal lines. How horizontal lines will map to W plane under the given transformation, or how vertical lines y is equal to constant will map to W plane. Circles r is equal to constant in z plane, how they map to W plane, and radial lines passing through origin, how they map to W plane. So, these are some of points of our interest. So, these curves are called level curves in z plane. Similarly, we can talk about level curves in W plane, that is, what is the curve for which u is equal to constant is an image, v is equal to constant is an image, or what are the curves in z plane that will map to circles in W plane, or circles are r is equal to constant, or what are the curves in z plane that will map to radial lines phi is equal to constant in W plane. So, for this, let us take an example. We have fz is equal to z square, and this means fz is equal to x square minus y square plus 2 times I x y. So, this is the real part and this is the imaginary part. And if we express this function in polar form, then z is equal to rei theta, or we can say w is equal to rei phi. So, this is the point z, but in W plane it will be z square. So, I am writing fz as w, let us call it rei phi. So, if I compare, then one can notice that r is nothing but r square, because z square is r square e 2 I theta. So, comparing the two, I will have r is equal to r square and phi is equal to 2 theta. By this I mean to say that this is z plane and this is a radial line, theta is equal to constant, this is another radial line, theta is equal to constant, this is a circle, z is equal to a constant, this is another circle, center at origin, but with a different constant. So, let us see how these 4 different curves will map on W plane under this transformation. So, let us see, this is the situation. When we consider this line, theta is equal to theta 1, then this suggests that this line will map to a radial line with angle equal to 2 theta. So, this radial line will move to this position. If this angle is theta, then this angle will be 2 theta. Similarly, this line will be mapping to this line, where the slope of this line is 2 theta 1, then slope of this line will be 2 times theta 1. So, the slopes are doubled. So, this is the mapping of this, where the slope is double of this, and this line will map to this line. Now, when we come to this circle, then this circle is r, but this is its image, its radius will be r square. So, this radius is different than this. If it is r is not equal to 1, then this will be the image of the interior circle, and then this circle will map to this circle. So, that is how circles are mapping to circles and radial lines are mapping to radial lines. Circles are mapping to circles, but the radiuses are changing, and similarly radial lines are mapping to radial lines, but their slopes are changing. So, that is how under this transformation these level curves, circles and radial lines will map to circles and radial lines in W plane. Now, many times we may be interested to know how this is u is equal to constant line and this is v is equal to constant lines. What are the curves which will map to these lines? So, if we will see our function x square minus y square is equal to u and 2xy is equal to v, then this line will be actually having a hyperbola on xy plane. The hyperbola is x square minus y square is equal to constant. Similarly, this line will be the image of a hyperbola in z plane, and that plane will be, that hyperbola will be xy is equal to constant. So, these are two different W planes. Here we have the circles and here we have the radial line, where we have the level curves. So this is u is equal to x square minus y square, and this is v is equal to 2xy. So this we have already discussed. Then we come to another function fz is equal to z raised to power n. Now in this case again I am writing r e I phi, the w plane, and this will be r n e I n theta in terms of r n theta, and from here we can say that r is equal to r raised to power n and phi is equal to n theta. So this means unit circle transforms into unit circle. So if we have a unit circle, r is equal to 1, then capital R will be also 1. Further, initial line theta is equal to 0, then phi will also be 0. So initial line will transform to initial line under this transformation. Circle r is equal to r naught transforms into the circle rho is equal to r naught raised to power n, and line theta is equal to theta naught transforms to the line phi is equal to n theta naught. That means the angle will be rotated and it will be n times the original angle theta naught, and line theta is equal to pi by n in particular will transform to the line phi is equal to pi. So if we consider this, then if this is the line with angle theta is equal to pi by n, then this line will map to this line having slope theta is equal to pi. So if we consider all such points here, then we can say that the region enclosed by this line and this initial line will be the upper half plane of W. So that is how this region will map to the upper half region of W plane. Now we discuss translation under the mapping. W is equal to z plus c1 plus ic2. So if I add a constant, this time a complex constant, then translation of points will take place. So let us say that z points are translated by distance c1 along real axis and c2 along imaginary axis. And if we consider transformation W is equal to bz, then this transformation means that W is equal to r e I theta, that is z, and let us say b is a complex number which can be expressed as b times e I c. C is a constant, b is a constant. So if we combine the two, it is the magnitude is br and the angle is theta plus c. So this gives me r is equal to b times r and angle will be rotated by c. So rotation of radial axis by an angle c will occur under this transformation, and the radial vector becomes br. It will be expanded or contracted depending upon the magnitude of b. If b is greater than 1, then capital R will be greater than r, so it is expansion, and if b is less than 1, then capital R will be contracted. So we have this situation. Now we will have a combination of rotation plus translation. W is equal to bz plus c. So rotation plus translation. So example is W is equal to 1 plus iz plus 1 minus I. So this is my B and this is my C. So under this transformation, let us consider this region, a rectangular region, and let me say that this point is 1 plus I. Then since I have to rotate, the point will be translated by a distance 1 minus I. So under this translation, this rectangle will move to this rectangle, and because of this term it will be translated and this will rotate an angle of pi by 4. So this will finally be moved to this position under this transformation. In another example, W is equal to iz, which is more simplified than this. Let us consider this infinite strip. This is x axis, this is y axis, and let us say this is of distance 1 and this is an infinite strip. So under this transformation, this strip is rotated by an angle pi by 2, and with this W becomes I x plus I y, and this gives me u is equal to minus y and v is equal to x, and that is how this strip will move to this strip in W plane. So, different regions are mapped to different regions. Now, we consider inverse function w is equal to 1 upon z. Now, we may notice that this function is analytic except at z is equal to 0, and when we write down this function as re I phi on w plane and r minus 1 e minus I theta, the right hand side, then this is equal to, this implies that r is equal to 1 upon r and phi is equal to minus theta. That means if I have a point on z plane as this, then this point will map to w plane here. By how I arrive at this point? See, this, let us say this is a unit circle, then this is a point outside the unit circle. So, 1 upon r will be, this r is greater than 1, so 1 upon r will be smaller than 1. So, this point will map to a point inside the unit circle. So, that is why this point is inside the unit circle. So, this is r is equal to 1 upon r, but what is the effect of this? Phi is equal to minus theta. So, if this angle is theta, then this point will lie on the line which is a mirror image of this line about this initial line. So, this line is will map to this point. So, this point will map to a point here, which indicates that it is inside, and it will lie on the line phi is equal to minus theta. So, this way different points will map to different points in w plane. Let me rewrite this. W is equal to u plus iv as 1 upon x plus iy, and we can simplify it. So, u is equal to x over x plus y square and v is equal to minus y over x square plus y square. This can be obtained by getting rid of this plus iy in the denominator. So, we will have u is equal to this expression and v is equal to this, and from here one can notice that if we have a circle, general equation of circle is a x square plus y square plus bx plus cy plus d equal to 0. It is a quadratic equation, and this will represent a circle when a is not 0, and when a is equal to 0, this part will not be there, it will represent a straight line. So, this is actually a general quadratic equation. It may represent a line or a circle. So, if we consider a line or a circle, then under this transformation it will map to this, and this again is a quadratic. So, it may be a circle or a straight line. So, after this transformation, this will be simplified to du square plus v square plus bu plus cv plus a equal to 0. So, this is again a quadratic, it will represent line or a circle. So, that the idea is the circles and lines in the z plane will map to lines or circle in the w plane. Different situations are possible. So, let us see what will happen in different cases. So, this is the curve in the xy plane and this is the curve in z in w plane. Then if I consider the case when a and d are 0, a is 0 means this part is not there, d is 0 means this part is not there. So, we have bx plus cy is equal to 0, it represents a line passing through the origin. So, a line passing through the origin in z plane will map to a line passing through the origin, because d and a being 0 in z plane, in w plane also it is bu plus cv. So, line passing through origin will map to line passing through the origin. However, if a is not 0 and d is equal to 0, then z plane will represent a circle passing through origin and w plane will represent lines not passing through the origin. So, that is how curves which are circles passing through origin in the z plane, they will become lines passing through origin in the w plane, lines not passing through origin in the w plane. In the next case, when d is not 0 and a is equal to 0, then in z plane they represent lines not passed through origin, and in w plane we will be having circles passing through origin. So, these are different cases, and accordingly circles and lines can be circles and lines, the level curves in Z plane will map to corresponding curves in W plane. Another transformation of importance is the linear fractional transformation. We define a linear fractional transformation W is equal to Tz as Az plus B divided by Cz plus D. You may notice that in the numerator we have a linear function, in the denominator also we have a linear function, and since we are dividing them we call it a linear fractional transformation. Here A, B, C, D are complex constants. Now this transformation is meaningful only when AD minus BC is not equal to 0, because if AD minus BC equal to 0, then we can write it as B by A is equal to D by C, and you can take A outside from this numerator and C outside from this denominator, and if this condition is satisfied then the two things will cancel out and what we have is simply W is equal to a constant. So this mapping is of not our interest, so we will consider the case when AD minus BC is not 0. Now this mapping one can always simplify it and write it as Z is equal to minus dW plus B divided by CW minus A, and that means for every W there is a corresponding Z in Z plane. That means the transformation is invertible, and invertible transformation is always 1 1 on 2. So we can say that T assigns each point of Z plane to a point in the W plane, and similarly T inverse assigns each point of W plane to a point in Z plane. The exception is a point Z is equal to minus D by C when C is not 0. This is the exception because when denominator is 0 then this mapping is undefined. So apart from this, this mapping is defined everywhere, and you can have a corresponding point in W for a given Z. Similarly for T inverse, it assigns a point of W plane to a point in Z plane, and the exception is this point. So the mapping is defined for all points except these 2 points. In fact, we say that this mapping, which is not defined for minus D by Z is equal to minus D by C, if we add a point infinity in W plane, then we can say that this mapping will map to infinity corresponding to point minus D by C, or minus D by C under this transformation will map to infinity in W plane. Similarly, we can say that A by C will map to infinity in Z plane. So W is equal to A by C will map to infinity in Z plane. So this way we are adding infinity in our complex plane, and the plane is then called extended complex plane. Then we define a fixed point of a mapping. A fixed point of a mapping W is equal to Fz is a point such that Fz is equal to Z. Example is the fixed points of Fz is equal to 1 over Z are 1 and minus 1, and this definition suggests that 1 will map to 1 and minus 1 will map to minus 1 under this transformation. And how we obtain this? You can simply write down 1 upon Z is equal to Z, 1 upon Z equal to Z, then it becomes Z square is equal to 1, and solving it will get Z is equal to 1 and Z is equal to minus 1. The next example will show that the fixed points of a linear fractional transformations are given by this expression. This can be obtained by writing Fz is equal to Z and simplifying the expression will get Cz square minus A minus dz minus B equal to 0. So we say that when the transformation Tz is an identity transformation when A is equal to D, this is 0, and B and C are also 0, B and C are also 0. So this equation is trivially satisfied. That means every point will map to itself, and such a transformation is an identity transformation. So, under this condition the linear fractional transformation will become an identity transformation. And on the basis of this we establish a theorem that a linear fractional transformation which is not an identity transformation has at the most two fixed points. One can notice that if this condition is not satisfied, that it is not an identity transformation, then the fixed points are given by this quadratic, and this quadratic gives us only 2 points. So, if we are having more than 2 points, then we say that the mapping is an identity transformation. So, this is what the theorem is. I am not giving you the proof of the theorem, just the theorem, and we can use it for checking whether a transformation is identity transformation or not. If a linear fractional transformation has 3 or more fixed points, then it is an identity transformation. So, this is the direct consequence of this. There is one more theorem which is used to get the linear fractional transformation, and we say we can specify 3 different points such that Z1 maps to W1, Z2 maps to W2, Z3 maps to W3, then there exists a unique transformation given by this expression. Again the proof is not included. These are the mappings by simple functions. Now I will discuss mapping by exponential function. So, if we have W is equal to Ez, then u plus iv is equal to ex plus iy is equal to ex cos y plus I sin y by the definition of exponential function, and this gives me u is equal to ex cos y and v is equal to ex sin y, and from here we say rho is equal to ex, phi is equal to y. From here rho is equal to ex in radial form and phi is equal to y, and that means lines x is equal to constant will transform to circles r is equal to ec, and lines y is equal to c dash will transform to radial lines y is equal to c dash. With this we come to an important concept of conformal transformation. A mapping is said to be conformal or angle preserving if it preserves angle between oriented curves in magnitude as well as in sense. By this I mean to say that if I have two curves, let us call them C1 and C2 in Z plane, and the angle between the two curves, which is the angle between the corresponding tangents, that is this tangent and this tangent, then if this angle is theta 1, so when these two curves will map to this curve and this curve in W plane, then their angles are preserved. So, that means if this angle is theta, this angle is also theta. They are preserved in magnitude as well as in sense. As well as the sense means that if we measure angle from C1 to C2, here also we will measure angle from C1 to C2. So, if this angle is clockwise, then this will also be clockwise. So, that is the meaning of angle preserving transformation, or we call it a conformal transformation. So, let us say that Zt is equal to xt plus Iyt is the equation of curve. It is an equation of curve because as t changes, t is the parameter of the curve. As we change t, we will have different points, and these different points constitute the curve. And W2 is equal to f of Zt is the image of this curve, and we write it as uxy plus ivxy. Let us say Z0 is a point on curve C, then the corresponding point W0, which is f of Zt0, is the image point of the image curve C star. Then dw by dt will be written as df by dz into dz by dt. From here is a composite mapping. So, dw by dt is equal to df by dz into dz by dt, and if C has a unique tangent at Z0, that means df by dz at Z0 is not 0. If it is not unique tangent, if this is 0, then we cannot find a tangent uniquely. So, this has to be non-zero. So, if df by dz is non-zero, dz by dt is not 0 because it is a curve and t is varying, dz by dt is not 0. So, dw by dt is not 0. That means, if the tangent is well defined at C, the tangent of its image will also be well defined. So, C star also has a unique tangent at W0, and from here we can find out that argument of dw by dt is argument of df by dz plus argument of dz by dt, which will be simplified to get argument of df by dz is equal to argument of dw by dt minus argument of dz by dt. And this means the angle of rotation for the transformation is same for all curves. That means if I take different curves, they will move different, their angle of rotation will be the same. And that means if we take two curves in z plane, then the corresponding two curves in w plane will also move in the same angle, and so the net effect will be the no rotation. So this gives us a theorem that the mapping defined by analytic function is conformal except at the points where f dash z is 0. So at f dash z 0 means the tangents are not defined, so there will be a problem, but for all other points, if the function is analytic, then the mapping will be conformal. So this is an important result, and the points where this is 0, those points are called critical points, and there the angle may not be preserved, but for rest of the curves the angle will be preserved. So this is an example. We consider fz is equal to z square. This function is analytic, which is conformal at all points except at z is equal to 0. So z is equal to 0 is z is equal to 0 is a critical point. One may also notice that f dash z is 0 at z is equal to 0. So this is a critical point, and this says that at z is equal to 0 mapping is not conformal, but at all other points mapping is conformal, angles are preserved, and in fact at z is equal to 0 radial lines there, when we draw two radius lines, the distance between them are doubled. This we have already seen in an example. So this function fz is equal to z square being analytic is conformal except at z is equal to 0. So with this we have covered a portion of complex variable where we have discussed function of complex variables, we have discussed some elementary functions and mappings, and finally we have described conformal mapping. That is it. Thank you.